This video will talk about radioactive dating of meteorites, talk about asteroids, near-Earth asteroids, and just a little introduction to, well, that's where this video will stop. The following video we'll talk about comets. But we'd like to know the age of the meteorites. We'd like to know the age of the solar system. So to do this in a scientific manner, we use the concept of radioactivity and radioactive half-lives. This chart shows us radioactive isotopes, and their half-lives are being displayed here with color. So in the blue area, seconds and minutes, and then we get here to 10 to the 20th seconds. That's in this dark red area. There are 10 to the 7th seconds in a year, so we're talking about 10 to the 13th years, extremely long number of years. There are some elements, and these red ones are just for practical purposes stable, these very dark red ones. But on either side of this dark red line, there are unstable isotopes with various half-lives. Some of those half-lives in the order of billions of years. So those will be our source of daughter products. When a radioactive isotope decays, it is the parent, and the isotope that is produced would be the daughter isotope. And astronomers then take samples of meteorite material to a laboratory and determine the percent abundance of the various radioactive isotopes, and can do calculations that give us an estimate of the age of the meteorite. There is an assumption that the meteorite has not been involved in some process that would inject new isotopes into the material or extract isotopes from the decay process. So we want to have a stable rock, not one that's been involved in an asteroid that had melting occurring. And this radioactive dating only applies for after the rock becomes solid. So there are quite a few of those meteorites available, and they have been dated. We use the concept again of the half-life. So in one half-life, 50% of the material is gone. So if this particular sample has a half-life of 1 year, then we have the situation of the 50% of the material is gone after one half-life. 25% of the material is gone after 2 years. That's 2 half-lives. And 12.5% is still remaining, is all that's left after 3 years. So 50% left after 1 half-life, 25% left after 2 half-lives, 12.5% left after 3 half-lives, and so forth and so on. This particular graph is set up with a half-life of 1 year. So astronomers measure the abundance of various isotopes, and not just with one set, but as many as they can, and determine the age of the meteorites. And fairly consistently, the meteorites come up with an age of 4.5 billion years. And that's our approximate time of the beginning of the solar system, when the rocks formed, when things became solid, roughly 4.5 billion years ago. Carbon-14 dating is more useful for archaeology. It's a shorter half-life, over 5,000 years. So it is not useful for dating the age of the solar system. So multiple isotopes are used, and there's various reasons for the lifetimes of stars that would imply billions of years for the ages of the stars as well, that the solar systems are tagging along with. So astronomers have confidence that the scientific age of the solar system somewhat over 4.5 billion years. So let's talk about impacts of asteroids. Again, NASA and other groups are trying to find asteroids that have orbits that cross the Earth's orbit, or at least perihelion is near the Earth's orbit. So we have discoveries coming back from the 1990s, and with better equipment, we're detecting more and more of the rocks. some of this is because we're detecting smaller asteroids. And I did kind of a rough estimate of what's being located here. And I went to the website of the Near-Earth Asteroid, neo.jpl.nasa.gov, neo.jpl.nasa.gov, and it shows the continuation of this graph. That in the year 2013, roughly 1,000 near-Earth asteroids were discovered. Well, combining the two bar graphs for 2013. This only has the first half of 2013. That website has an updated chart. So roughly 1,000 were discovered in 2013, and in 2014, about 630 near-Earth asteroids have been discovered. Again, the search is getting more efficient, being able to find smaller asteroids. For the really dangerous asteroids, we're talking a kilometer and larger, that would have a devastating effect near where they impact, and to a wider extent as well, some effect on the Earth. We're seeing the number of new discoveries drop down, and it is hoped that we're getting a better catalog, that we found the ones that are to be found for the most part. But there's still a few a year of these dangerous asteroids that are found to have orbits that bring them inside the Earth's orbit, so they cross the Earth's orbit at some distance. It doesn't mean they're right in the ecliptic, doesn't mean that they're a strong likelihood of hitting the Earth, but they're in our neighborhood at some point in their orbit. So we want to try to track them, and maybe we can make some kind of preparation. Maybe we can discover some way to deflect them. And there are planned missions to asteroids to land on an asteroid and determine what it's made of and its strength, its structural strength. We need to know that if we're going to somehow deflect it, push it out of the way. There have been visits to asteroids. Good science is being done with the asteroids. But impacts have a problem for the Earth. That here we have 4,000 feet diameter, over half a mile, and 570 feet deep. This impact about 50,000 years ago, if I remember correctly. But as these impacts occur, the crater is 10, 15, maybe 20 times larger than the rock that crashes into the Earth. Depends somewhat on the density of the material that's coming into the Earth as to how effective it is at making a crater, and the speed that the rock comes in with. And they're going to be traveling on, in the ballpark of 40,000 miles per hour, I think is the number. That's just off the top of my head, so don't quote me on that. But they're moving at large speed. They carry a lot of energy, and they release much more energy than a nuclear weapon releases for these dangerous near-Earth asteroids. So one of these objects comes in, one larger than the one that made this crater in Arizona. As the impact occurs, and it throws up tremendous amounts of material into the atmosphere, some of that material then re-enters, rocks re-enter, and as they re-enter the atmosphere, they're hot, and they can start fires around the world as this debris is ejected from this local impact site and takes its own little miniature trajectories, orbit, not quite orbit because they're coming back into the Earth, but as the material descends back down, and what goes up comes down if it's not moving past escape velocity. This material, as it comes back down, is hot as it re-enters the atmosphere and can start fires around the world. Also, the impact itself can do some chemistry in our atmosphere and create nitric acid that would create an acid rain and would be poisonous and a bad environment to be under that type of rain. So we have the near-Earth objects. We're trying to keep track of them to try to prepare and try to deflect. And some other examples of these large craters. There's a few hundred of these large craters around the world. We have about 60 miles in diameter here, for this crater in Canada. In 2008, there was a dramatic impact in Siberia, and it's estimated that 80 million trees were knocked over from the explosion that occurred, and the area 820 square miles. So that's a little bit under 30 miles on a side if it's a square. 820 square miles, so 30 square miles on a side where the trees were knocked down. A big event. It created barometric pressure changes that were observed in England, where this event occurred in Siberia. Then bolides, where we have small pieces of rock, asteroids, bigger than sand. It doesn't just make a meteor trail, it makes a brilliant flash of light in the sky as the asteroid disintegrates in the sky. So from 1994 to 2013, a plot of those occurring, you can see that we have these objects entering the Earth's atmosphere on a regular basis all over the Earth, and carrying a significant amount of energy, but these are not making craters. The object is exploding in the Earth's atmosphere as it heats up. 2013 in February, there was a very large event like this in Russia. So Chelmsky, you can pronounce it better than I can, but this boloid that came across here, this photograph was taken 120 miles away from this city, and just shows you that it was a big vapor trail in the sky as it came through here. You ought to do a search on YouTube for this name and play some of the videos. It was pretty dramatic. The explosion occurred about, I think it's something like 15 miles up in the atmosphere, maybe a little lower than that, but that's my memory. And that explosion created a pressure wave, sound wave, that blew out windows, set off car alarms as the cars were jostled. But several people were injured from flying glass of as windows were knocked out, and buildings damaged by the pressure wave that came from where the region where the asteroid exploded. So we have that. So there we are with a little bit more on asteroids, a little reminder of radioactive dating, and some of the effects on Earth if we'd have an asteroid impact. Large craters, a lot of debris thrown up in the atmosphere. I should mention too that when something like this and bigger occurs, dust can be thrown up in the atmosphere and can block sunlight. If it's a really big impact, it can block sunlight for a year, which would result in loss of vegetation, disruption of the food chain, and probably had a role to play with the extinction of the dinosaurs, so that's getting to be a little bit controversial. About 65 million years ago, there's some evidence that there might have been an impact that could be one of the reasons that you don't have dinosaurs, hunting season for dinosaurs. We just have hunting season for deer and pheasant. So keep doing your own reading, bring some questions to class. But that's where this video will stop with our discussion of asteroids.